core, having completed the intro gates yesterday. And now we're directing our attention to this one, knapsackLight. Now, before we get into this, you might be looking at this and thinking, well, that sounds a little familiar. Haven't we seen that one before? And yeah, I mean, this is another one of the ones that was featured in the intro. It's also here in the core. I'm pretty sure it was task 39 from the intro. So at some point we'll take a look at that. But if you remember, I mean, basically when we were looking at this one in the intro section, we used it as an opportunity to sort of get into the concept of dynamic programming. I was about to say to introduce the concept of dynamic programming, but we actually introduced it in task 33, strings rearrangement. So you may benefit from taking a look at that. I mean, if you're not familiar with dynamic programming, if you're not familiar with bitwise operators, I'd probably recommend watching video 33 from the intro, strings rearrangement. It's a really, really rich one. It's quite long, but it covers a lot of important topics. So we're probably going to take a look at our previous solution for knapsackLight. Not quite yet, but sort of after we get into it, we'll take a look at that and we'll see if we can sort of adapt it, if we can learn anything more from it. The main thing, I guess, is just like for these ones that are repeated tasks, like for ones that appeared in the intro and now they're reappearing in the core, I sort of want to look at them a bit differently than the first time we went through them. You know, like I want to try to apply something new to them. Just, you know, try to be a little less repetitive sort of thing. So I guess with all that said, we might as well dive in, take a look at what knapsackLight is asking us. Okay, so the first thing I have to say about this one is this is kind of like an adapted version of like a very, very popular dynamic programming challenge. I mean, this is one of the most classic dynamic programming tasks out there. So yeah, we'll probably talk about that in the not so distant future, but for now we're going to take a bit of a different look at it. I mean, okay, sorry, before we go any further, I should probably describe what it's asking us. So we found two items in a treasure chest. The first one weighs weight 1 and it's worth value 1. The second one, it weighs weight 2 as value 2. Okay. And basically the idea is that this is where the knapsack comes into play. We've got a knapsack on and it has a maximum capacity of max W. And basically what we want to determine is what's the maximum value we can get away with given our capacity here. So it might be a situation where like the weights are too big to carry both of them and we're going to have to choose between these two, try to choose which one is going to be more worth it. Maybe we'll be able to take both. Maybe we'll be able to take neither of them, right? Maybe our max W is way too small and we can't carry either of them. So all of these are possibilities. Now, we're calling it knapsackLight. The light part of this is because there are only two items. So the more traditional version of this problem has us looking at arbitrarily many values, arbitrarily many weights. So like we could have 100 items, let's say, all with different weights and values. And the sort of dynamic programming algorithm allows us to very efficiently find the maximum value that we can get away with. Now, before we go any further, I just want to say, in case anyone's having an issue with the wording here, I'm not sure how common the term knapsack is. It's one that I sort of grew up hearing, but basically it means a backpack. My dad used to call it a pack sack. I'm not sure if there's anyone else in the world who calls it that, but anyway, this is also, I think, known as the rucksack problem, so I'm not sure if that's just a different language term for the same thing. Anyway, if anyone knows, feel free to let me know in the chat or in the comments. As for now, I guess we should probably talk about this note here. I mean, basically, like, they're just saying there's one copy of each of these things. We can't, like, bring duplicates or anything like that. It's not like we have infinitely many of these, although that would be sort of a variation on the knapsack problem. So, you know, that would be an extra exercise, I guess, if we want to look at it that way. But for now, we'll just take on this problem as it is. So, I guess we might as well start with just the most naive interpretation. We'll look at this in terms of just like, not really a smart algorithm. Well, okay, I guess maybe in some ways this is the smartest way of doing it, but I just want to sort of look at it kind of brute force, just considering all the possibilities. We're probably going to have a lot of ifs in here. So we could say something like if we can accommodate both items, we'll do that, right? So if weight 1 plus weight 2 is less than or equal to max W, if we can carry them both, then let's just return value 1 plus value 2. There we go. So if we can carry both of them, let's get both of them. Simple as that. Okay, now if this ends up being returned, so if this if statement is true, if it ends up executing this code, it won't go any further. So we don't need to worry about putting like an else or anything like that, because if we make it past this if, if we don't make it past this if, we're not going any further in the code. So no need for an else. We can just say if, actually at this point, let's say const heavier. Should we do something like this? Actually, no, let's actually make it an if. So we'll say if weight, or if value 1 is greater than value 2. Okay, so this is the case where value 1 or item 1 is more valuable. Okay, now keep in mind, we're only making it this far if we can't accommodate both items. Okay, so if we can do this, then we'll say, okay, if weight 1 is less than or equal to max W, then we're going to return value 1. And otherwise, we'll say, okay, well, in that case, if weight 2 is less than or equal to max W, then we'll return value 2. Okay, so this is the case where item 1 is more valuable, so we're sort of prioritizing item 1 in the sense that we first want to check if we can accommodate weight 1. If we can't, because keep in mind, if we can, this will just return and we're done. So if we can't, then we'll check this one and we'll say, all right, well, we couldn't accommodate the more valuable item. Can we at least accommodate the less valuable item? And if we can't accommodate that, then we might as well just go ahead and return 0. And we can't accommodate anything at that point. So we might as well run this, I guess, and see if we're passing some of them. So half of them. All right, it's better than nothing, but it's not perfect. So let's figure out what's going on with this one. So we've got value 1 is 5, weight 1 is 3, value 2 is 7, weight 2 is 4. We've got a max W of 6, which means we couldn't carry both of them. They have a combined weight of 7, so that's too much. So then what do we want to do? Well, basically that means we'd end up over here with this if. So if value 1 is greater than value 2, well, no, it's not actually. So we need to consider that other case. What if value 2 is the greater value? And actually, I was copying that, but here, might as well just do an else because that speaks for itself, right? So this would mean that item 2 is more valuable. Okay, so then what do we want to do in that case? Well, pretty much the same thing as this, except we're going to flip the order now because we're going to say, well, item 2 is more valuable. So if we can accommodate weight 2, let's prioritize that one. So if you're wondering why the order here is important, basically it has to do with the fact that, like we were saying before, if the first one ends up being true, it's not going to execute the second one. So, if we end up returning this one, we're not even going to consider that next one over here. So for something like this, basically the order matters because we want to first check if we can take the more valuable item, and if not, then we'll check the other one. So let's try running this. We'll see if that works. And yeah, that seems to be working. We'll just get a bit more space in there. And let's check the hidden test. There we go. Okay, so not too bad. Nice job. We'll close that. And great. I mean, we're passing all the tests. Not much left to say about this, but we might as well take the opportunity to sort of try out some different ideas here, different ways of looking at it. So in particular, first, let's look at just another way we can sort of view this problem. Okay, so same sort of thing. We're not going to generalize it to like a greater problem or anything like that. But, we've been doing some OOP stuff, some object-oriented programming lately. And I kind of want to stay with that theme. I want to use some objects here because we sort of have these similar things. Like in particular, we've got these items, right? I keep talking about item 1, item 2. Technically, there isn't anything in the arguments that specifies like an item 1 or item 2. So I'm going to make this thing called item. Okay, so this is going to be a constructor, which is why I'm using a capital I for item there. This is sort of like sentence case, I guess. Or not quite. I'm not sure what you call that case. It's not camel case because the first one is capitalized. Yeah, I'm not sure. If anyone knows, let me know. Anyway, for now, basically what we're going to say is just something very, very simple. We're going to say this dot value is assigned the value of value. Oh, jeez, that was a tough one to say. This dot weight is assigned the value of weight. There we go. Okay. So pretty straightforward. I mean, nothing too surprising about that one. These are basically just our items. And then we can say something like this. Const items is assigned the value of, and I'm going to make this new array. It's going to contain our 2 items, basically. So new item with a value of value 1 with a weight of weight 1. And then the second item here is going to be another new item with, you guessed it, value 2 and weight 2. Okay, cool. Whoops, there we go. Just fits. Nice stuff. So those are our 2 items here. And we could do something like, just to see if this is working, we'll say items at 1 dot weight. Whoops, weight. So this should be giving us weight 2, basically. Let's see, weight 2 is 4. We're getting 4. If we check this one, weight 2 is, yeah, okay. Weight 2, okay, is weight 2 always 4? Weight 2 is 3. There we go. Okay, cool. So that seems to be working. It's giving us the value we're sort of expecting. You might be wondering, like, well, yeah, that's cool and all, but why? You know, why bother with this? And I guess I would say, just to sort of keep things organized, you know, like if we had a whole bunch of these items, it would be kind of inconvenient to have like value 1, value 2, value 3, value 4. You know, we don't want to have like a billion arguments or something like that. So like if this was more general, we could basically just have an array of items. Each of those items would have a dot value, a dot weight. Just, I think, makes it a little more organized, a little easier to work with. So I'm going to delete this return before I forget. Just for the next time we want to run it, I don't want any weird return values. So, okay, we've got our items here. Now, I've got another thing I want to write in here. So let's write basically a constructor for a knapsack object. Okay, and our knapsack will have a capacity. I guess that's sort of one of the defining things about this knapsack. And basically, the idea is we'll just do like we were doing with the other object. This dot capacity is capacity. Okay, cool. What else are we going to have here? Well, we'll do this dot contents, and maybe we'll start with an empty array there. This dot weight, and this will be just sort of like how much weight is in the backpack at the moment. This dot value, so the value of everything that we have inside the backpack right now. And we'll do a few methods as well. So these are properties we'll use for the knapsack, and we'll do something like maybe like capacity. Remaining capacity, let's do that. Yeah, remaining capacity. Now this is sort of right on the borderline of being like maybe a too long variable name. You know, I don't like to make them too long, but it's good to be descriptive, so I guess it'll pay off. So basically what we're doing here is if we want to know the remaining capacity at any moment, we'll just take the capacity of the knapsack, like what we started with. Basically, we're going to use max weight for that. And we're going to subtract from that the current weight of what's inside the backpack. So basically, it's just what's left over. And we're running that, we're making that a method. We're making it a function attached to this object so that so it's always sort of up to date. You know, we don't need to keep updating like a remaining capacity property or attribute. It's always just going to take the things that it comes from and just subtract those. So take the capacity, subtract the weight that's already in there. There are other ways we could do this. I mean, we could just have a variable for remaining capacity instead of having weight in there whatsoever. Maybe that would be better. I don't know. But for now, we'll just do it this way. Okay, and then we'll have a few more of these. We'll say this dot take is going to be a function which takes an item as its argument. So this is where things are going to start to get a little more interesting in terms of how these objects are going to interplay with each other. So basically, the first thing we want to do is this dot contents dot push, I guess we could say. Yeah, and we'll put the item in there, and then we'll say this dot weight plus equals item dot weight, this dot value plus equals item dot value. Okay. So keep in mind, it's an item. It's going to be an item type of object. So that means it's going to have a value property and it's going to have a weight property, which means I can do item.weight and item.value. I'm going to add both of those to the current weight and value of the contents of this knapsack over here. And then also the contents itself, right now it's an array, and we're basically pushing this value into the array. So that's pretty neat. But I actually want to change this a little bit. Something about having the array here, I feel like it would be more appropriate to use a set. Because these are all going to be unique items anyway. We don't have to really worry about there being like multiple copies or anything like that. These are all going to be unique. I feel like set is just going to be a little more appropriate here. This.contents.add. We're saving one character. I know that's not a huge deal, but I just kind of prefer the way set works for these kinds of things when we're just adding and removing them, when we don't care about the indices of them or anything like that, where we're basically just keeping almost like an unordered list of items. I feel like set is really appropriate in those kinds of situations. So that's an ES6 built in case anyone was wondering. It's a really nice one. I've been getting a lot of mileage out of it. Okay, cool. So we've got this dot take. So basically this is when we want to take we've got the knapsack, we want to open it up, take a new item. And maybe we should build in some kind of check here, like if item.weight is less than or equal to remaining capacity. Like maybe that would be a good thing to do, but we'll build that in on like outside of the object. So for the actual algorithm that we're going to be running on this thing, we'll do the check at that point just to make sure we don't overflow the knapsack. So I don't know if it'd be better to actually include that logic in here. Maybe like make it throw an error or something if you do try to overload it. Yeah, that'd be neat maybe. But for now, let's just move on. So we've got this dot take. Now technically we're just assigning these as variables, so we should probably put the semicolons at the end here. Okay, and then next one, we've got this dot take, we'll do this dot remove. So in case we need to remove an item from the knapsack. So function item, and we're basically going to say this dot contents dot delete. So that's the syntax for a set. Not something we could use for an array, so this is another sort of advantage to using a set here. And then we'll say this dot weight minus equals item dot weight, and we'll say this dot value minus equals item dot value. But there's sort of one issue with this one. The issue is that for removing here, we need to make sure that we're actually removing, something that's in the knapsack. If it's not in there already and we try to remove it, the way set works, it's going to try to delete it. If it can't delete it, it'll just move on. It won't throw an error or anything like that. Although this actually does return Boolean, and it represents whether or not it was successful. So basically, if it did delete, if it did find the item in the set and was able to delete it, then this is going to return true. If it didn't find the item and therefore did not delete anything, then this is going to return false. So we can sort of use that actually, because we wouldn't want a situation where, well, actually, you know what? Let's demonstrate. So basically, we could say something like, okay, first of all, const knapsack, lowercase, is assigned the value of new knapsack, uppercase, with a capacity of max W. Okay, cool. So then maybe we could do something like knapsack.take items at 0. Okay, and then we'll say return knapsack dot weight. Yeah, let's try that. Okay, so 5. And it's because we're taking the first item, so that seems to be working. It's updating the weight in here. It's weighing it down by 5, whatever units these are, maybe kilograms. And then we could also take a look at like maybe value. And in this case, let's actually say knapsack.take. Let's take both of them. Let's just combine them both in there. So there we go. We're getting both of the values, so 10 plus 6, we've got 16. Now, of course, we shouldn't be taking both of those. And the reason is because if we were to do remaining capacity here, we would find that it's actually negative. We've taken too much. It only has a capacity of 8, and we've loaded it up with a full weight of 9. 5 plus 4 is 9. So we have a negative remaining capacity. That's not really great, so maybe we will want to think about building up some kind of error throwing behavior for take there. We'll see. But anyway, for now, okay, so that's not great. So maybe we want to actually remove one of these things. So we'll say knapsack.remove items at 0. Okay, so we'll remove the first item. And so now what do we have? Remaining capacity, we have 4. Why do we have 4? Well, we started with a capacity of 8. We added the first item, we added the second item, we removed the first item. So basically the second item is the only thing left. It has a weight of 4. 8 minus 4 is 4. So yeah, there should be 4 remaining in terms of the capacity here. So cool, that's good. It seems like the remove is working. Now let me just demonstrate one more thing here. What if we tried to remove something that had, let's say, a value of 10 and a weight of 20, let's just say. We'll try to remove that thing. Well, it's not giving us any sort of error here or anything like that. It's saying we now have a remaining capacity of 19. Well, that's great. We could fit a lot more stuff in here. But I think this is kind of misleading, because if we were to do this, let's do a console log of knapsack.contents. Is that going to work? I know it's kind of strange to display a set sometimes, but yeah, okay. So we've got 2 items in here. Item with a value of 10, weight of 5. Item with a value of 6, weight of 4. And if we actually do the console log before the removal as well, we'll compare to see if it actually removed anything. And no, these are the same contents. So if it's not actually removing something, we shouldn't actually be changing the remaining capacity here. We shouldn't change the weight and the value. So what we want to do for the remove is we want to say, well, if we were able to delete this thing, then under those circumstances, that's when we want to alter the value and the weight, and not if we weren't able to. So let's try running it now, and what we find is we still have that remaining capacity of -1 because we weren't able to remove anything here. So that's good. That's working a bit more like what we want here. So important that we put this if in here to make sure that we actually are successfully deleting that from the contents. Now, one thing I want to do here, this is actually a test. I'm not sure how this is going to work. I have a suspicion, and I have an idea of how I want it to work, but notice for the first item here, the value is 10, the weight is 5. So I'm going to just try to remove an object that has a value of 10 and a weight of 5, and we're going to run the tests on that. What's going to happen when we do that? Well, we still have a remaining capacity of -1, and we still find that it didn't remove this item here that had a value of 10 and a weight of 5. Why is that? Well, because it's not the same item. This is an item that happens to have the same value and weight. It has the same characteristics as this other item in here, but it is not itself the same item. They're different things. So this is just another item with the same attribute. So that's actually kind of a good thing. It's almost like every item has its own sort of signature. Okay, so this was just sort of a demonstration. Let's close this up for now. I want to let's actually kill the return even. I want to add in, I guess, one more method here. So maybe we don't want to just remove one particular item. Maybe we want to remove them all. So we'll do this.empty, and this is going to be a function. It's not going to take any arguments. Doesn't need them. It's basically just going to remove everything. So this.contents, we're just going to reassign it. New set. Okay, empty it all out. And then this.weight, 0. This.value, 0. We just dump it all. Okay, we get rid of everything that was inside the knapsack, and that might be useful for us in terms of how we want to go through this one. Okay, so we got our items, we've got our knapsack. Now, what do we want to do here? Basically, we want to go through our items for const item of items. Nice opportunity to use a for of loop. It always feels good. So basically what we'll do with this one is we'll say, well, if the weight of this item is less than or equal to our knapsack's remaining capacity, well, in that case, let's take it. Knapsack.take item. Okay, and maybe we'll just put in the braces here just since it all didn't fit on one line. You see, it's because I made this one so long, remaining capacity. So, it's a struggle, you know. You want to make your names descriptive. You don't want them making the lines so long that it makes the code unreadable. So it's a balance, like all things in life, I guess. Okay, so that's our if statement. So that's if the item will fit. But what if it won't fit? So we'll put in an else here. And this is basically what we're going to do in the situation that the item does not fit. So if the item doesn't fit, then basically I want to say, all right, well, would it be worth it to remove the item that's in there already and replace it with this one? So we'll say, okay, well, if item.value is strictly greater than the current value of the knapsack, you know, what's in there already, in that case, we're going to basically empty it out and take this new item, right? So we'll do knapsack.empty. We'll execute that. And then we'll do knapsack.take this new item. Okay, cool. And then at the end, I guess we're just going to return the value, the total value that we found here. Knapsack.value. Great, let's run that. We'll see how it goes. Oh, okay, so I'm passing some of these, 75% of them actually, but some of them not. Let's take a look at what's going on with this one. So value 1, value 2, so we got 10 and 11. Max W is 1. Oh, we're saying that we can take the 11 here, but we actually can't. So we do need to still check here. Well, do we have space for that other item? So basically, it's not just that the value of this is greater than what's in there already. We need to also say, all right, well, not just that, but the weight of this item is small enough that we can accommodate it. It's less than remaining capacity. Less than or equal to remaining capacity. It'll fit is what we're trying to check. Okay, so let's run that. And, oh, we're still not getting the right answer. Okay, cool. So I wonder why that is. Oh, you know what? Yeah, okay. It's not a matter of remaining capacity here. It's actually just a matter of capacity. Because remember, we're resetting this, right? Like we're starting over. We're going to empty it out and then put this new item in here. So basically what we want to check is if we were to totally empty it out, would this item fit? So is it less than or equal to the total capacity, you know, like the max W that we have here? Yeah, right here, our max W, our capacity. So is that going to work? And yeah, it looks like it's going to work. Okay, so we got a lot of stuff here. I mean, this is definitely more lines than the previous one. It's overkill, I'll give you that. It's more complicated than it needs to be, but as we can see, it passes the hidden tests. And it sort of illustrates some of these object-oriented programming concepts. So it's a good exercise, I guess I'd say, in that regard. Okay, so what else do we want to do here? I was kind of going to get into a discussion about closures and stuff like that, but maybe we'll save that for now because I don't feel like this would be the ideal introduction for that. I mean, let me know in the chat if it's something you really want to see, but maybe what we'll do for now is let's actually take a look at how we did this the first time around. So we want to go back out and we're going to go back to the intro, actually. So not just the intro gates, the actual intro section over here. I think it was 39. Let's try to find it. Yeah, 39, knapsackLight. So this was our dynamic algorithm here. So maybe we'll take a look at that and sort of try to refine it. Yeah, okay. We'll copy that. Well, hey. We'll bring it into the core. This one over here. And here we go. We'll paste this in. I think we need to close up the brace here. We're gonna make that, I'm gonna give it a 2 so it's not the same thing. And I guess first, let's run the tests on this. Okay, so yeah, that's working. I'm just gonna be right back. I'll leave the code on the screen, I guess. You can try to soak this in, but I'm just gonna be right back. Okay, sorry about that. So basically, we've got our dynamic programming algorithm. You've had a chance to sort of take a look at it, soak it in at this point. So let's take a look at what we're doing. We start with values and weights, and we're basically just putting each of our values and weights into these arrays. And I mean, the reason is like, basically, if we had a whole bunch of these values, if we had a whole bunch of these weights, this is sort of the way it would probably be presented to us. I think traditionally that's sort of the way they serve up this problem. The full version, the heavy, knapsack heavy, we call it. So basically, they'd give us an array of values, an array of weights. They would be the same length, and they would represent the values and weights of each of the objects that or items that we're dealing with here. Okay, and then I have this array DP. It stands for dynamic programming, because this is our dynamic programming algorithm, and the idea is that it's a very efficient way to solve this problem for any number of items. Okay, so basically what are we doing over here? We're saying we've got an I value. It's going from 0 to up to and including values.length. So this would go 0, 1, and 2. Okay, so keep that in mind. It's basically one more than the length of this is how many times it's going to iterate. Okay, so what are we doing with this? Well, we're saying let this row be an empty array. And then we've got this other thing, limit, which is going from 0 up to and including our capacity. And we're declaring a maximum, which is starting at 0, basically for each of these things. So, okay, first things first. We're sort of going through each of our values here, right? Well, each of our items, I should say. So this is a loop that's iterating through each of the items. This is a loop that's iterating through basically every capacity up to and including our actual capacity here, max W. And we'll find out why we're going to do that in just a sec. But basically, it's dynamic programming, so we're sort of using kind of like a matrix of values. So I guess the most efficient way for me to describe the principle behind this is that in order to get the maximum value that we can get for a capacity of max W, we're first going to calculate all of the maximum values we could get for any set of items, any subset of items here, and any capacity less than or equal to this one. And we're going to use those previous calculations to calculate our new values. So this is sort of the fundamental principle behind dynamic programming or backtracking. We're trying to cut down on repeated calculations, so we're not repeating ourselves. That's basically it. Okay, so we're starting with maximum here. We're saying if I is greater than 0. Now notice, like if I is greater than 0, this whole thing. If I is 0, then we're just going to go ahead and push max. It's 0. So we're going to start out with a row of all zeros. That's going to be it. In fact, yeah, actually, there's a console log over here, so we can take a look at what we're actually getting. And okay, kind of a sizable thing here, but notice that our first row is all zeros. If we look at this one, our first row is all zeros, or I guess I should call this our 0th row, but it's all zeros is the point. And I mean, no surprise based on what we're seeing here. So that's because of the if I is greater than 0. And we sort of want them to be all zeros for a reason that we're going to encounter in just a sec. I guess maybe I'll make this a little bigger, and we'll just use this as an example. Yeah, cool. So we've got our first item has a value of 5, a weight of 3. Our second item has a value of 7 and a weight of 4. Okay, so basically the idea is for our 0th row, we're basically trying to find the max value that we can get for, let's say we didn't have any of these items. We're not considering any of these items yet. For row number 1, we're only considering item 1. Okay, so and each of the columns here represents our capacity. So our capacity is actually 6, but if we were to look at the indices of our columns here, it would be 0, 1, 2, 3, 4, 5, 6. Okay, so 6 is like, this would be for a capacity of 6. And notice the last value we're getting here, the 7, well, that's the actual answer here, and that's not a coincidence. So that's if we were considering the full-on capacity of 6, and we were considering all of the items up to including 2, this would be the answer we're looking for. And that's why, as a response, we're doing return dp.pop.pop. You know, so pop giving us this last array here, popping that gives us the last value in that array. Okay, but I don't want to get too wrapped up in that for now. Let's just talk about how this is actually going to run, why we're getting these kinds of values, what they represent, and all that good stuff. So basically, we're going through the first row, and we're basically saying, no matter what your capacity is, if you have no items, you're not going to get any value out of that. So it's 0, 0, 0, 0, 0, 0. Okay, so then what if I was 1? So now we're considering item 1. And, you know, everything up to and including item 1 is the idea. Okay, so we're sort of restricting the focus here. We're saying, okay, well, at first, we don't want to consider all the items. We just want to consider, well, none of the items. Then we want to consider just the first item, then just the first and second item, then just the first, second, and third item, etc. If there was a third item. But that's sort of the principle here, okay? So that's what we're doing with our dynamic programming. Okay, so basically, we're going through this. We're going through each of the limits here. Let's say I is 1. We're working on row with index 1, so technically the second row here. And we're basically saying, okay, well, let's increment the limit. So if the limit is 0, then, okay, first of all, I is greater than 0, so we'll get into this. We want to say max is going to be reassigned the value of dynamic programming at I minus 1, so basically the previous row, just this right here, at the value of limit. So basically it's kind of saying, all right, well, the maximum value that we can get, basically let's assume that it's just going to be the same as the maximum value we were able to get with no items, you know, so these are all zeros anyway. So this is not really doing anything when I is 1 because max was 0 already. We're just making it 0 again. And then we want to say, well, if weights at I minus 1 is less than or equal to limit. So, okay, what's this all about? Weights at I minus 1. So the first thing I should say is weights, it's this array here, right? Weights at I minus 1. Well, keep in mind, we're only entering this loop if I is greater than 1. So the I minus 1 basically means if I is 1, we want to be looking at item 1, but it has an index of 0 here, not an index of 1. So that's why we're doing I minus 1. So we're doing 1 minus 1, that would give us 0. So weights at 0. It's this thing. It's our weight. Okay, and maybe we can modify the code and actually do like weight and value. So actually, yeah, that's probably a good idea. In here, let's just say const weight and value. Do we have those already somewhere? Just, I don't think we do. Yeah, I don't think we do. Okay, so weight and value are, and actually I should probably spell that right. Okay, so weight and value, we're going to do a destructuring assignment here, and we're going to say that they're going to be equal to weights at I minus 1 and values at I minus 1. Okay, we might as well just get those in there. And then instead of having to say weights at I minus 1, we can just say weight. Same with this, we don't need weights at I minus 1, we can just say weight. And then same with value. We don't need to say values at I minus 1, we can just say value. Okay, so is that still gonna run? Let's just make sure I didn't break it here. Yeah, okay, it's still running. I can't remember which example we were looking at. I don't think it was that one. Yeah, I think this is the one. Okay, so basically we've got our weight, we've got our value. This is just for the current item, you know, the weight and value of the current item. Let's make a bit more space here. And then basically what we want to ask ourselves is the weight of this current object, is it less than or equal to the limit here? Now keep in mind the limit is not the same as max W. It'll go up to max W, but it's not exactly equal to max W. It's basically like the column index here, right? So as we're going through here, well, we know what weight is. In fact, you know what? This right here, we probably shouldn't be recalculating that so many times. We could put it up here because that stuff's not going to change. I mean, that's based on the I value. So yeah, that stuff's not going to change. That should still work, right? Yeah, cool. Let's put the space there instead. Okay, great. I'm liking this so much more already. Okay, so we've got our weight and our value. Now what's going on with this down here? So we're saying if weight is less than or equal to limit, and yeah, that's the test we were looking at. So if the weight is less than or equal to the limit, well, what's the limit? The limit starts at 0. Well, the weight's not going to be less than or equal to 0. It's going to have some weight to it. I guess we should probably check the constraints here. Yeah, I mean, it's going to be at least 2. So this is definitely going to be 0 as well. We get to this point and we say, okay, now the limit is 2. Can we accommodate weight 1? Well, it has a weight of 3, so no, we can't. Okay, so we iterate, and now the limit is going to be 3. And we'll say, all right, is the weight, which is 3 here, is that less than or equal to the limit, which is also 3? Yeah, actually it is. So we'll say max in this case is going to be max.max of whatever max was, and keep in mind it's taking its value from the previous row, so it starts out as 0. So the maximum between 0 or value, which is 5, plus dp at I minus 1 at limit minus weight. Okay, so dp at I minus 1, that's basically saying previous row, this one right here, right? We were using that up here. So max was, okay, so our limit is 3 right now, right? So we start with max being dp at I minus 1, so previous row at limit, which is 3. So it starts as 0. Okay, so max is currently 0. And then we say, or if this is a greater value, it could be value, so 5, plus the previous row at limit minus weight. Now we can do limit minus weight because we know that weight is less than or equal to limit. We know that limit is at least as big as weight. So when we subtract them, we're not going to get a negative value. We're not going to get something less than 0. So it's still going to be within the range. So here we're basically saying, all right, well, this value here, it's going to be the maximum of 0, the value we got over here, or 5 plus this 0 over here. Why this 0? What makes me say that? Well, it's because it's limit minus weight. In this case, limit is 3, weight is 3. So that would give us another 0. The previous row at 0, it would be this one over here. So 5 plus 0 is 5. That's why we see a 5 in this one. Okay? So we move on to the next one. We say, oh, well, you know, the limit here is 4, so we could accommodate this item. So weight is less than or equal to limit. And again, do we want to use the 0 that we have up here, or do we want to use 5 plus the 0 that we have over here? So in other words, 5. Yeah, we'll use the 5. And same for all of these. If we can afford to take the 5, we'll afford to take the 5. We will take the 5. Okay, cool. So then after that's done executing, we say, okay, I should have mentioned this earlier, but we're always going to push the max value into the row, whether it ends up being 0, whether it ends up being something else, we're always going to push that in there. And then we're done with our row at the end of this. You know, we get to the end, we say, oh, okay, dp.push row. Let's put it into this big old matrix over here. Okay, cool. So then after that, we want to move on to our third row here, our row with index 2, and it's going to represent our last one here since we only have 2 items. So basically the idea is that now we're looking at our item 2, so we have a value 2 and weight 2 is what we're looking at, and that's what we're going to get when I is 2. This is basically going to execute and say, oh, okay, I want this one and that one. Great. So we've got our weight and our value. Now, let's frame that a bit better. Great. So now I is 2. We're going to start again with a limit of 0. So basically, if the limit is 0, we're not going to be able to take the item. I mean, I is greater than 0, so this stuff's going to execute, but it's not really going to work. It's not really going to do anything for us. I mean, basically, we're going to say max is just whatever you had at that same limit on the previous row. So we've got 0 here, we've got 0 here, we've got 0 here. We get to this point, and now limit would be 3. And keep in mind, our weight is 4. Okay, so we get to this point, and we say, all right, max is 0, I is greater than 0, so max is going to be assigned the value of 5, because that's what we had on the previous row. And then we say, if weight is less than or equal to limit. Well, is it? So weight is 4. Is that less than or equal to 3? No, it's not. So we're not going to execute this part over here. We wouldn't be able to, because limit minus weight would be -1. It wouldn't be an index, a valid index on our previous row. So we're not going to do that. Instead, we're just going to push the 5 in here. So that's why we have a 5 there. But if we move on to the next one, now limit is 4, and we say, well, is weight, the weight of 4, is that less than or equal to our limit of 4? Actually, yeah, it is. So we say, well, okay. Either we could take whatever value you have on the previous row, so either the 5 that we have here, or the value plus the previous row at limit minus weight, which would be 0 in this case. So it would be 7 plus 0. Well, 7 plus 0 is 7. That's actually better than the 5 we would get here, so that's why we see a 7 here, as well as here and here, and that gives us our final value. So it basically means we're going to take the second weight. Now, that's basically how this is all working. Again, this would work if we had an arbitrarily large capacity, an arbitrarily large number of items. We could have a whole bunch of values and weights, and this method would still work. This algorithm would still work just fine. Now you might be looking at and thinking, it seems like heavy overkill for this problem. And yeah, I agree with you. I'm trying to make it general so that even if it was knapsack heavy, even if it wasn't just restricted to 2 items, we'd still be able to handle it. That's the main thing. But the other thing is, you might be looking at this and thinking, well, it still feels like overkill though, even if you do need like arbitrarily many of these, because you're just looking for that final value, right? So like, why keep a whole matrix of all this stuff if you don't really need it, you know, if you only really need this final value? And I mean, the main thing is so that we can do this stuff, so that we can look back at the previous row, look back at our, you know, limit minus weight, so like the whole way back through that previous row. But then again, something we could notice about this is the fact that as soon as we move on to the next row, the only row we care about is whatever the previous one was. We don't care about, like, you know, I want to know about the previous 2 rows, or the you know, the one before last, or something like that. We never do that. We only do dp at I-1. So I want to modify this now. I want to switch this up. Basically, what we're going to do is we're going to start. Well, okay, we're going to make dynamic programming here. Instead of it being a matrix, we're just going to keep 1 row at a time. So we're going to modify this so it only keeps 1 row at a time. So instead of doing dp at I-1 at limit, we just do dp at limit. And then we're just going to redefine what dp is at the end. We're going to just say dp is assigned the value of row instead of dp.push row. So that's going to be sort of our idea here. So let's do that. So basically, we're going to start this out. Instead of being an empty array, let's just say array at max w plus 1 dot fill 0, because that's what it's going to start as, right? And that also means we can start this at 1, because we already have the first one. Remember how we were always getting that row of zeros? No longer. Okay, which means, well, sorry, no longer do we need to do it in here. It's taken care of now. This is going to be a row of zeros with the correct number of columns. So that's great. It also means we don't need to check if I is greater than 0, because I will be greater than 0 in this case. So we don't need that stuff. We can simplify this a little bit. So now I'm looking at this and I'm thinking, okay, do we need max is assigned the value of 0? Could we just say, didn't mean to do that. Could we just say let max be assigned the value of this? Let's find out. So let max be assigned the value of that. And it's not going to be dp at I-1 anymore. It's just dp at limit, right? Because it's just a single row now. It's not like a whole bunch of them. So there, and it's not dot push, it's assign the value of. Okay, and instead of dot pop, we want just a single dot pop. We do want the dot though. Just because it's one array now. It's not a whole matrix, it's just one array. Does that work? Let's try that. Yeah, it works. Okay, and if we take a look at what we're returning, it's just that final row. You know, it's just the last one we dealt with. So that's good. I actually like that a lot better because it feels like we're using up so much less memory. I mean, you might look at this and think like, well, you know, one array versus 3 arrays, not that big of a difference. But if there was like 27 items here, this would be the difference between 1 array and 28 arrays. Like, that's kind of significant. That's kind of significant. It's of significance. Huh. Spelling error, jeez. Anyway, okay, so basically that's still giving us the right values. It's getting a little more efficient here. It's starting to look a little nicer, so that's pretty good. Let's see, could we do this any differently? Well, yeah, first of all, this would be a constant, and we could use destructuring assignment. I forget exactly how it's called, but yeah, I think this is called a destructuring assignment, but it's basically where we assign these two things together as one sort of like, yeah, it looks like we're doing an array here, but really we're just assigning values and weights both at the same time. And does that work? Yeah, that still works. Okay, so that's pretty good, you know, that's pretty not bad. Okay, and then we're doing this thing over here. Now, what's this all about over here? So we're making a new row. I wonder if there's a different way we could do this. So we've got our weight and our values, our weight and our value. We've got this loop that's running. It's basically going all the way through from a limit of 0 to all the way to max W. So, I'm wondering if there's a different way we could do this. Because basically what we're doing is we're looking at this, right? dp at limit. Max is starting as dp at limit, and then we're basically saying if we can do this, you know, if it's within range here, then we'll do this. Well, maybe we could just go right to the math.max, you know, like let max be assigned the value of, and then we won't even check this weight limit thing here. We'll just say what's max originally? It's dp at limit, so we'll do this. And then basically for this part, we'll say, well, okay, if you can't add the value to that thing, then we'll just say, or 0, you know, because basically, like, if it doesn't have this thing, that's just going to be null. We add a value to null, not going to work. So we'll just say, or 0. We'll just do math.max of that. And will this work? I don't really like that overhang there, so maybe we'll make a change. I guess for now, let's just do that. That's probably easiest. Okay, so let max be this, row.push this. So basically, we're just doing a row.push of this thing, right? I mean, that's what max is. Okay, so is that going to work? Yeah, it is. But now I'm starting to notice something about this. I mean, like, row... Okay, check it out. Let row be assigned the value of, it starts as an empty array, right? And then we basically just fill it up with all the values from what's already in our DP array here, right? Our dynamic programming array. So basically, all of our row values are just going to be this, right? Just like our math.max of what's already in there. Dynamic programming at limit. Dynamic programming at limit minus weight. Okay, so let's think about this for a sec. I'm wondering if instead of this, if we could just do something like let row be assigned the value of dynamic programming dot map. Okay, so we're going to map this out, and we'll say we'll have the actual value. Yeah, the value that we have in there, right? So, or no, sorry, we already have value. So let's, okay, we'll call that V. Maybe we'll call it M because like it represented the maximum at that spot. And then I guess this next one is what limit is, not limits, limit, right? Because that's what the index was. It was the limit. So then from there, dp.map, it's basically going to map to this thing, right? So is that going to work? And then dp@limit, well, that was just m, I think, right? It was just, yeah, the value that we had before. Yeah, is that the same thing? Like, could I just delete this and have that work the same way? Yeah, still works. So dynamic programming is assigned the value of row. Well, I mean, could we just say dynamic programming is assigned the value of dynamic programming of map, all that stuff? Let's find out. Yeah, that's still working. Okay, so that's pretty not bad. Yeah, that's pretty not bad. I kind of like that. I mean, maybe we can make it more efficient than that. I'm not sure. That's a tough one. But let's see. I mean, yeah, we could probably do like a for each or something like that instead of this for loop over here. We could probably handle that part more efficiently, but you know what? I think I'm probably satisfied with this one. Let's see if it passes all the hiddens. Yeah, it's passing all the hiddens. So, okay. I think this is probably pretty okay, pretty good. So, yeah, let's move on from here, I think. Yeah, this is good. Let me know if you have any questions, comments, or concerns on any of this stuff. I think we've made our dynamic programming algorithm a little more efficient. I mean, it doesn't take up nearly as much memory as it would the previous way we were doing it, storing that whole matrix instead of just the sort of one row at a time that we need. So this is kind of cool. I like that. Great. Okay, so we'll finish up with this one. Nice job. We'll go back to